Hello and welcome to lecture 53. We are discussing about the turboprop engine. In last lecture, we were discussing about single spool turboprop engine which was having the configuration like this, where the turbine it is connected with the compressor as well as with the propeller by using say gearbox. And we were discussing about the power transmission or say work transfer. Initially we have understood like power transmission for the compressor, that's what is given by mechanical efficiency into turbine work. Later on that work it is being transferred to the gearbox, that's what is given in terms of difference of work. Then later we have discussed about the gearbox efficiency, and then we have considered say propeller efficiency. This is how the transmission of power, that's what we have discussed in last lecture. Very important aspect we were discussing is in terms of transfer of work. Here in this case, we know this turbine it is being used for rotating compressor as well as propeller. And what amount of work, that's what is being transferred for both the cases, it is little tricky to understand and to calculate. One more thing is in exhaust we are having nozzle. So this nozzle also is contributing some amount of thrust, that's what will be generated by this engine. And in order to understand that part, we have taken the approach where we have considered say ideal enthalpy drop, that's what is from say 4 to 9s, and from there we have considered say some fraction alpha, that's what we have considered as a power split factor, that we have discussed about say alpha into delta H fraction, that's what we have considered for the turbine, and remaining amount, that is 1 minus alpha into delta H, we have configured for our say nozzle. So this is what all we were discussing in the last lecture. Now let's discuss about say some other approach. So here in this case, if we look at say we are having say single spool turboprop engine. Suppose if I consider it is having say inlet area say A in, exit area we can consider say EA exit. Same way if we consider say this engine is fitted with the aircraft which is moving with say V aircraft velocity, the air that will ingest inside is with V in velocity. Similarly, suppose if I consider say mass flow rate that we are writing as m dot in, and our inlet pressure, that's what is given by P in, that is atmospheric pressure at whatsoever altitude it is flying. Here in this case, if we consider this propeller, that's what is exchanging the energy, and that we are representing in terms of delta P0. This delta P0 is nothing but this total pressure rise, that's what is happening across our propeller. So let's put that in terms say my exhaust total pressure from the propeller, that's what is P0 in plus delta P0. This delta P0, that's what is by designer's choice. And in exit we can say we are having exit pressure to be P exhaust, that is also atmospheric pressure, and we have exhaust velocity, that's we are representing as a V exhaust. Now let's try to understand this, what exactly the mean is. Let me put it here. Suppose if I consider this is the plane, I say it's an inlet plane, or we are applying say Bernoulli's equation in front of the propeller, then that we can represent in terms of P0 equal to P plus half rho V square, that is at the inlet, that's why it is suffixed with in. At the same way I can apply Bernoulli's equation at the exit of my propeller, that's what is given by P0 exit, it is equal to P exit plus 1 half rho V square exit velocity. Now we cannot apply Bernoulli's equation say for the propeller, say at the entry condition and at the exit condition, this is what we are representing. Now let's put this as say delta P0. This delta P0 is nothing but outlet pressure minus inlet pressure. If I'll be representing in terms of what equation we have, then it will be given in this form. Suppose if I consider say my exhaust pressure and inlet pressure, that's what is my atmospheric pressure, then this equation that will be simplified in terms of half rho V exit square minus V inlet square. You will surprise what is the reason why are we doing these things. So let's try to understand what is the meaning of that. Since this is what is my P0, we have our fundamental equation. This fundamental equation, it says my force, it is given by pressure into area. This pressure I am representing in terms of say P0 exit into exit area minus P0 inlet into inlet area. For the sake of simplicity, let's consider my inlet area and exit area to be same. If that's the case, then we can represent that my thrust, it is given by delta P0 into my area. This delta P0, that's what we know from earlier equation. It is half rho V exit square minus V inlet square. And if I'll be simplifying this equation, it says my thrust which is generated by this propeller, it is given by 1/2 rho A V exit square minus V inlet square. So rough estimation of the thrust generation by the propeller, people most of the time they are using this formulation. They are calculating based on this equation. Now there are fundamental equations, fundamental explanation, that's what is available for the propeller. So when we are doing design for this engine or when we are doing cycle analysis, most of the time people they are considering initially the propeller characteristics. And from there also we can move forward in order to calculate what will be the thrust generated by the propeller, what will be the amount of power that's what is required in order to rotate that propeller. But since this course is dedicated for the gas turbine cycles, and that's the reason we will not be discussing that in more detail. But you can understand this is also one of the way to calculate the thrust that's what is generated by the propeller. Now in order to understand this say whole formulation, we can go with say momentum theory or actuator disk theory, blade element theory. We can also go with say combined propeller theory. This all explanation that's what is available in basic books, we can say in propulsion books or gas turbine books. You can go through that part if you are interested in going with more detail how exactly people they are doing their calculation on the basis of propeller configuration. But at this moment for our rough estimation, you can say this is what is fairly enough to understand what we mean by the thrust that's what is generated by the propeller. So this is also one of the way. We have discussed thrust calculation in earlier formulation where we have calculated the power, then based on that power we have calculated our thrust. So this is also one of the way as I said. Now let's move towards the next kind of configuration. So here if we look at, we are having single spool turboprop engine. This single spool turboprop engine, as we have discussed, this is having the configuration in which my compressor and propeller they both are on the same shaft, that's what will be rotated by the turbine, and that turbine we have discussed, it is named as a gas generator. So here are some of the engines which are existing. So Rolls-Royce T56 engine, that's what is been used for C-130 Hercules say aircraft, where it is connected with this kind of configuration where we are having say axial flow compressor, that's what will be followed by the combustion chamber, and we are having say axial flow turbines. In line to that there are many engines. Suppose if we look at TPE331, that's what is generated or developed by Honeywell. If we look at here in this case we are having two centrifugal compressors, that's what will be followed by combustion chamber, reversible angular combustor, then we are having say turbines, and this turbine that's what is connected with this shaft using the gearbox, and that's what will be rotating our propeller. So mainly for Hindustan Turbo Trainer 40, this engine that's what has been used. Now here we need to understand one thing, what all engines we were discussing in terms of turbojet engine, turbofan engine and turboprop engine, we must realize here the purpose of this engine, it is to rotate the propeller, and if possible we can extract some amount of thrust that can be generated by the nozzle, but the major focus that's what is for the generation of power. Okay, and that power we are using for the rotation of a propeller. So now let's look at here. So here this is what is a kind of configuration, you can say. We are having say axial flow compressor, that's what will be rotated by say axial flow turbine, and we are having say discontinuation, or you can say we are having say different spool. We have understanding about the spool. So you can say here we are having one spool on which compressors and turbine they are connected. We are having other spool, that's what we say it is my power turbine or free turbine, that is connected with the propeller by using this gearbox. Now for turboprop engine, the most challenging part, it is not only to design these compressors or turbines or combustion chamber. Most challenging part it is to design the intake, and we know how we have placed this intake. That's what will be giving us what will be the efficiency of the engine, what will be the performance of the engine. Here in this case, this is what is CT7 engine. If you look at, they are having special kind of configuration where in case bird it will get ingest, that can be kept inside by say bird catcher. There are applications where it is being used in the desert area, so they are having say particle separator, that's what is used to separate say sand particles from the going inside the engine. So this is representing the similar construction in a detailed way. So now you can say we are moving towards the next kind of configuration where we are having two spools. So let's look at what we mean by two spool configuration. Here in this case, if we look at, say we are having our compressor that is connected with the turbine. Secondly, if we look at, we are having secondary turbine, or we can say power turbine. This power turbine that is only connected with the propeller. So this is the kind of configuration we can say it's two spool turboprop engine. Okay, so this is representing the cut section of AE2100. That's what is being used for Lockheed Martin C310J Super Hercules. Such 4 engines are connected with this aircraft. Now here in this case, you can imagine the power generated by this engine is huge power, and that's what can be configured by having say number of stages for compressor as well as number of stages for the turbine. And we have our reduction gear, that's what is connected with the propeller shaft. Okay, similar kind of configuration it is also possible to have with axial centrifugal compressor combination. So GE 338 and Pratt & Whitney 150 are of such configuration, where in place of having axial flow compressor which is been rotated by the turbine we can say HP turbine. Okay, similarly we will be having say axial flow compressor that will be followed by the centrifugal compressor, and that's what will be rotated by HP turbine. We have discussed earlier, there is a special requirement of compactness of these engines, and in order to reduce the number of stages for axial flow compressor, we are going with say centrifugal compressor. But the challenge with the centrifugal compressor, as we discussed earlier, it is to turn the flow from axial to radial direction, and again we need to configure our flow in axial direction because we will be having our turbine which are of axial configuration. So let's look at, as we go ahead we will get the understanding of that part. Here in this case we are having two spool configuration in which we are having say our HP turbine which is connected with the HP compressor. We are having the LP turbine which is connected with the LP compressor as well as our propeller shaft. So this is representing the cut section. You can see we are having say more number of axial compressor stages. So this is representing how my flow is going inside. So we will be having the inlet, that's what is of this shape, from where the flow which is going inside. Then as we have discussed, we will be having the rise of pressure. Again it will be passing to the HP compressor where we will be having rise of pressure again, and later on we are having combustion chamber followed by the turbine and exhaust nozzle. Okay. Now let's look at what all are the other possibilities. Here in this case, if we look at, we can say what all we have discussed, that's what is configured. People used to say booster on HP pressure spool. So here in this case, this compressor we can define as a HP compressor, and LP compressor, as we have discussed earlier also in week 6, week 7, say we can configure this compressor, we can say this compressor as booster compressor. So here in this case, booster compressor and my HP compressor, they both are on common shaft connected with the HP turbine, and my LP turbine, that's what is used to rotate only propeller. If we look at here carefully, the number of stages for this turbine, they are more. The requirement is to rotate the propeller at a lower speed. So the whole work, it is been extracted with more number of stages in order to reduce the rotational speed of the turbine, as well as that will help in order to reduce the rotational speed of the propeller. Anyway, gearbox, it's most essential part for the turboprop engine, and that's what is creating the trouble or the challenge for the design. So here in this case, if we look at, this is the different kind of configuration. If we look at carefully, we are having the intake, it is placed somewhere here. So from here, the air, that's what is going inside. We will be having, say, axial flow compressor. That's what will be followed by the centrifugal compressor, and here in this case we are having, say, turbine. Say this turbine, that's what is rotating, say, all the stages of the compressor. But at the same time, if we look at on the rear side, we are having free turbine or the power turbine. That's what is connected with the shaft on the rear side. Now here in this case, the exhaust from this nozzle and the design for this nozzle, that's what is very challenging. Just look at here, these nozzles, they are been deflecting the flow like this. The purpose here for the nozzle, it is not for the thrust generation. If you recall, when we discuss the configuration, when we are fitting with the engines on the aircraft, that where also we have discussed the same configuration. Okay, this is what is the most famous engine, that's what is PT6 engine, PT6E configuration. Here also we are having, say, our axial flow compressor, that's what will be followed by the turbine, and on the rear side we will be having. So you can imagine the engine, it is placed in this way. So puller and pusher kind of configuration, what all we have discussed, you need to keep that in mind. How we will be using our propeller, how we will be placing our propeller, and accordingly my inlet, that's what is decided with. So if you recall, we have discussed based on the intake, we can say whether my engine, it is pusher kind or puller kind of configuration. Okay. Now let's look at here. Here in this case, if we look at, we have a different kind of configuration where the turbine, HP turbine, that's what is connected only with the HP compressor, and LP turbine is connected with the booster compressor as well as propeller. So here, like it is the designer's choice as per the requirement, as per the space available, and as per the cost of the engine. People, they are designing with a different kind of configuration. So there is no super spacious discussion about, say, how and why these people, they are configuring like this. But one can imagine there is a special requirement of the size of the engine, weight of the engine, cost of the engine. That's what all will be deciding how we will be configuring our construction for the engine. And that's what need to be decided when we are doing our cycle analysis, because that's what is the very first step. Okay, so we need to look, we need to read all the configuration which is available, which is defined, and accordingly we need to move forward with. Okay, now let's look at here. So this is representing the Rolls-Royce RB53 Dart engine, where if we look at carefully, we are having our inlet, that's what will be followed by two centrifugal compressors. They are connected with, say, here the flow, it is entering axially it will be going out radially. Again, that's what is been passed axially. So this is what is a flow channel. That's what need to be designed carefully, because you can imagine my flow, it is turning too much here and then it is moving inside, where there are more chances for my pressure to drop, and that will increase the losses. But when we are looking for the compact size of the engine, then we have this kind of configuration. That's what is possible with. So basically, when we are doing our cycle analysis, it is not necessary to understand what kind of compressor or what kind of turbine it is being used. But like, since we are studying this course in detail with detailed discussion, it must be discussed here, and that's the reason why we have incorporated this part. Here, if you look at, say, this is representing how my flow, that's what is happening. We are having, say, our inlet that will be followed by the, say, centrifugal compressor. From here, the flow is entering inside the second centrifugal compressor, and here in this case, it will be passing through the reverse annular combustor that will be followed by these turbines. Let me put the point here. Now, what pressure ratio, that's what is generated by this centrifugal compressor, it's a function of rotational speed. And here in this case, if we look at, since we are using this centrifugal compressor, and if we will be rotating at lower speed, then my diameter of the compressor will be very large, and that's where my size of the engine will be increasing. The size, in the sense, we can say the diameter of this engine will be increasing. In order to avoid that kind of situation, they have configured that in such a way that in the front side, they are using, say, reduction gear with different stages, which will take care of rotational speed of propeller, as well as the size of the engine, as well as the configuration of the compressor. So be careful, just look at carefully. If you are interested in understanding and learning how this design it is being done, we already have NPTEL course which is discussing about, say, design of this axial flow compressor for different configuration. In near future, we will be having a new course where we will be discussing how to design these radial machines. Basically, what we mean by radial machine is, say, centrifugal compressor, mixed flow configuration. This all will be coming very soon. Okay. Now, let's look at here. So, if we look at carefully, here in this case, we are having 3-spool configuration also is possible. What we mean by 3-spool configuration is, we are having, say, here we have HP turbine, that's what will be rotating my HP compressor. We will be having, say, LP turbine. Sometimes people, they used to say IP turbine, or IP turbine means intermediate pressure turbine. If you recall, when we have discussed 3-spool configuration for turbofan engine, we have discussed this point. So here this LP turbine, it is used to rotate the booster compressor or, say, LP compressor. And we have power turbine. Okay, this power turbine, that's what is connected with the propeller using the gearbox, and we will be having the nozzle that also will be contributing the thrust. Okay, now suppose if I consider this engine, that's what is having large length, or say length and the diameter, they both are higher, then people, they come up with the other solution. Just look at here. So here, if we look at carefully, this also represents the 3-spool configuration. What is the difference here? Here we are having booster compressor, we are having, say, HP compressor, but look at carefully, here in this case, we have our centrifugal compressor also attached with. So you can imagine, when we are looking for large capacity engine, large power requirement is there, huge power requirement is there, then you need to go with this kind of configuration, because fitting of this engine on wing, that's what is very challenging, and we have discussed all these aspects during our second week when we were discussing about the intakes. Okay, so we need to be very careful in terms of what all configurations we are looking for. But for initial stage, when we are doing our cycle analysis, that time we are interested in what is the pressure ratio for booster compressor what will be the pressure ratio for HP compressor. Based on that, maybe in later configuration we will be selecting whether we will be going with all axial compressor or the combination of axial centrifugal compressor, or we will be going with say all centrifugal compressor. All possibilities are there. Okay. Now let's look at here. So this configuration is of a different type. If we look at carefully, what is the configuration here? Say we are having our HP turbine. This HP turbine, it is connected with the HP compressor, as well as if we look at carefully, this LP compressor that is also been connected on the same shaft. Okay. Now if we look carefully, this turbine, this power turbine, what we are looking at, that's what is connected only with this propeller. Okay. And what is the beauty of this? So if you recall, we were discussing about say intercooler regenerator kind of configuration. We have discussed this in week 9, where we were discussing new innovative kind of engines, and there we have discussed what all research are going on for intercooler and regenerator configuration, where we have discussed there is one more possibility to apply this logic for the turboprop engine. So this is the configuration. We have understanding, this is what we say as our intercooler. So this intercooler that is connected between say our LP compressor and HP compressor. Then we will be having say regenerator. So the high pressure, high temperature air which is coming out from the HP compressor, that will pass through this heat exchanger. That's what is called say regenerator. This regenerator again will be raising the temperature, and that's what will be input to the combustion chamber. And if you recall, we have discussed what all are the benefits of say intercooling and regenerative kind of cycle. Can you quickly plot the TS diagram for this configuration? Let's see how much you have recalled from the previous week, because very earlier say last week only we have discussed about this configuration. So let's try to look at, just put it at the earliest part. Let's see what all we have. Say we have our inlet condition, this is my intake. Then we are having LP compressor. The next component what we have is our intercooler. So this intercooler, that's what will be decreasing the temperature of the air. This decreased temperature and the pressure air, again we are supplying to say HP compressor. From HP compressor, suppose if I consider the conventional cycle without regenerator, then we will be having the heat addition which is happening at constant pressure, and that will be raising the temperature, and that temperature we say it is HP turbine entry temperature or turbine entry temperature. We are having our expansion which is happening in HP turbine. Next expansion, that's what is happening in our power turbine. Later on, if we look at carefully, here we are having the regenerator. What this regenerator will do? It will exchange the heat between cold air and hot air. So hot air is, or hot gas is nothing but the flow which is coming out from the turbine, and cold air which is coming out from our compressor, that will get heated up here. So that's what we are representing in terms of regenerator. Okay, so one side it is cooler side, other side it is getting heated up, and from 7 to 9, that's what is representing my exhaust nozzle. So here in this case we have discussed a lot about the configuration earlier in turbofan engine. Here the benefit, as we have discussed, is in terms of what we say power requirement, that's what is reducing. At the same time, the heat, amount of heat addition, if we are not having say regenerator, then that amount of heat addition will be say T04 or H04 minus H03. But by incorporating this regenerator, this amount of heat addition will be H04 minus H035. So that's what is a benefit, and that's what has attracted the attention for the researcher, engine developers to move towards this kind of configuration. With interest of time, we will not be discussing in detail. If you are interested, you can search the literature available in open source. If we discuss particularly for the turboprop engine, not much details which are available in open literature, though these engines are of most widely used, because we have discussed for regional transport aircrafts, for the small aircrafts, this is a main choice, but you will not find much literature. That's what is pertaining to this turboprop engines. Okay. With this, let's move towards the comparison for turbojet, turbofan and turboprop engines, because we have started initially with the turbojet engine, then we have discussed a lot about turbofan engine, then we have discussed or we are discussing at this moment for the turboprop engine. So let's take the comparison with 5 main parameters of interest. Very first parameter is our flight speed. So we need to configure, say, turbojet engine, that's what is providing the higher flight speed. For turbofan engine, as we have discussed, it is moderate speed, and for turboprop they are flying at low speed. So here if you look at this turbojet engines, that's what we are using for fighter aircraft. Even for commercial aircraft, we are able to achieve very high flying Mach number, maybe in the range of 2.2. Similarly, turbofan engine, what we are using for commercial aircraft, that's what is around say 0.8 or 0.85, and for military aircraft, that's what has reached to 2.2. Turboprop engines, they are flying at say low Mach number in the range of 0.4 to 0.6. Okay, it depends on what is our application. Next important parameter for the selection is thrust to weight ratio. If we configure turbojet engine, that's what is having say a thrust to height weight ratio to be high. For turbofan engine, that's what will be moderate or lower, and for turboprop engine it is lowest one. The amount of fuel used for thrust, that's what is say moderate for turbojet engine, and it is lowest for turbofan and turboprop engine. And that's where our commercial aircraft, that's what has come into the picture. We are discussing about the fuel economy. When we are configuring the fuel economy, that time the choice is with turbofan engine and turboprop engine. Very next, that's what is in terms of thrust to airflow, what we can say as a specific thrust. This is highest for the turbojet engine. It is moderate for both turbofan as well as turboprop engine. Now when we are discussing about the ground clearance between engine and the ground, that's what is good for turbojet engine. It is moderate for turbofan engine, but we have discussed when we are moving with high bypass ratio or very high bypass ratio or ultra high bypass ratio engine, then my ground clearance, that's what is the issue with turbofan engine. For turboprop engine, this ground clearance is a major challenge. That's what is poor. Okay, so this is what all we are discussing in terms of say relative term. Be careful what all we are putting in terms of point, it is varying from engine to engine. But in general, this is what is our understanding. Now let's look at what all we are looking for and what all we have discussed till now for last 9 lectures, and this is what is say 10th week. So it says when we are discussing about the turbojet engine, my thrust, it is lower for the lower speed. That's what was a limitation we have discussed for turbojet engine. Higher specific thrust, fuel consumption, then it is having low specific weight. So weight to thrust ratio, that's what is lower, and its frontal area also is lower. So that's what has attracted the attention towards the movement for turbofan engine, where we are having higher thrust at lower speed. That's what is a major concern. Thrust specific fuel consumption is better compared to our turbojet engine. The noise issue is not the major concern. If we are discussing about the propulsive efficiency, then the propulsive efficiency is higher compared to turbojet engine. It depends on what speed we are flying with. Similarly, let's look at about the turboprop engine. The attraction is because of higher propulsive efficiency at the lower speed. We have discussed this. It is correlated with the exit velocity and flight speed. Then it is more complicated and heavier compared to our turbojet and turbofan engines, because we have a special device we say is a gearbox. That's what is creating the trouble for that. The specific fuel consumption, it is lower, and that's the reason why more attraction is focused towards a application of this engine for regional transport aircrafts. And the noise because of propeller, that's what is highest for this. Okay. Now with this all, let's move towards say one numerical. Say just take the data, take this information with you. Say we have regional passenger aircraft which is cruise at altitude where ambient pressure and temperature are 38 kilopascal and minus 30 degrees centigrade. The aircraft is powered by twin shaft turboprop engine. When we say twin shaft, remember we are having the free turbine kind of configuration. That's what is being used for rotating our propeller. The cruise velocity is 320 kilometers per hour. Following data which are available, it says the propeller efficiency is 82%, compressor efficiency is 84%, burner efficiency is 98%, efficiency of the HP turbine is 85%, efficiency of LP turbine is 90%. Consider mechanical efficiency, that's what is 99% for HP turbine and 95% for LP turbine. Gearbox efficiency, that's what is 99%. Nozzle efficiency is say 98%. Okay. Now here in this case, the core mass flow rate is given, it is 2 kg per second. The inlet total pressure recovery factor is 0.98. Compressor pressure ratio is 6.3. Maximum allowable turbine entry temperature is 1212 Kelvin. The total pressure loss in combustion chamber is 2%. Consider the heating value of the fuel as 42,000 kJ per kg. The design power split between LP turbine and engine nozzle is 0.95. Just understand what is the meaning of that. This is what we say in terms of our parameter or say factor, power split factor alpha. You need to calculate the properties of working fluid at all stations, thrust force, thrust specific fuel consumption and propulsive efficiency. So let's look at this information. We can say this is what is our configuration. You can quickly plot your TS diagram for this configuration, and this is what will be the TS diagram. Here in this case, some fraction it is given, that means we need to take care of what we mean by say our delta H. Okay, but be careful here in this case, this delta H is at different location. My HP turbine, it is used to rotate my compressor, and my LP turbine, it is used to rotate only propeller. So you need to be careful about this configuration. Okay, so let's discuss about the hint point and then we will stop with. So the hint here, for the inlet we have information about the flying velocity, entry temperature, entry pressure and pressure recovery factor. Based on that we can calculate what will be the exit pressure and exit temperature from the intake. We have our next component, it is compressor. For compressor we have information about the pressure ratio and efficiency. We can calculate what will be the exit total pressure and exit total temperature. We have our component, that's combustion chamber. For the combustion chamber, say we have data, that's what is delta P0, my calorific value of the fuel, CP value, maximum turbine entry temperature. That's what is being used to calculate what will be the pressure and the fuel air ratio. Here in this case for HP turbine, the information that is given, it says we are having say efficiency about turbine entry temperature, what is the turbine efficiency. we can calculate what will be the exit pressure and exit temperature from the HP turbine. Now the next component, that's what is very important, that's what is my LP turbine. Since we are not having more information available in terms of what is the power requirement from the propeller, then here we need to go with the configuration as we have discussed. We need to calculate our delta H ideal, and from that delta H ideal we need to calculate what will be the power, what will be the pressure, what will be the temperature for this power turbine, and based on that we can calculate what all will be the parameters for the nozzle. Once we have all this information available with us, we can easily calculate what all are the performance parameters. So I'm sure this information, that's what is more than sufficient for you to solve this numerical. Let's build the confidence in terms of solving the numerical, because for last 9 weeks we are discussing the cycle analysis, and I'm sure now you are confident enough to solve this kind of numerical. That's what is little different, but it's all you need to learn with. Okay, so here we are stopping with this lecture. We will be discussing the solution for this numerical in next week. Okay, and thank you very much.